Okay, so that's spectral theory. Okay, if A is Hermitian, then there exists a unitary matrix U that diagonalizes A. Okay. This is the last theorem, okay, for this section. Okay. So, not as, I think that, yeah, normal matrix. This is the matrix. Okay. So this one is like a fast one. Okay. So we know like if there's a unitary matrix U. Okay. So basically, we already know like any matrix, we have for any matrix A, okay, there exists a U such that okay, U H A U equal to other triangle. Okay. Now let's put the U H A U H. Okay. So this is supposed to be, you know, you reverse it and then put H. So U H A H U H H. I mean that will be U. Okay. And this A H, because A is a Hermitian, so it's U H A U. So this is T, right? By the way, this one is T H, right? So if T H equal to T, what does it mean? Okay. Remember, T is upper triangular, right? T is upper triangular. And the TH equal to T, it doesn't mean T is Hermitian, okay? Not only that, it means T is diagonal, right? 你现在已经有下面一半这里，然后你下面一半跟上面一半这个，它 transpose 是一样的，代表上面一半，就是 diagonal 上面的那一半也是，对不对？So TH equal to T because T is our triangle, so we know like T. So if A is a real symmetric matrix, then there exists orthogonal matrix U that diagonalizes A. So if A is a real symmetric matrix, it means A is kind of Hermitian, right? Hermitian, but so there exists orthogonal matrix U that diagonalizes A. I mean, so not much to really talk about. Basically, just follow everything that we have done. But now it's all the discussion confined in like the real number domain, and that's it. Okay. So give an example. this is like an example of A. You can see that, it's a symmetric matrix, okay? And you can do calculation and basically find like the eigenvalue, eigenvectors, and then obviously like because it's a real symmetric, so these eigenvectors they must be orthogonal, and then you try to make them orthonormal, and then that's pretty much about it. And you have your U, and your D will consist of the diagonal element will be like those like eigenvalues. Okay. So yeah, it's basically E plus lambda squared minus lambda, so it's lambda is -1 and 5. So for -1, there are 2 eigenvectors. For for 5, there's 1 eigenvector. So you try to create like do like Green-Smith process. So lambda 1 is going to be this one. Okay, basically just divide like W1 by the next of W1. W2 basically like it's this one. So basically you just need to remove whatever that W2 is X2. Remove the part that's like the projection of remove the projection of X2 on X1, and then you get W2, and then you need to make W2 like a unit vector. So that's like that. W3 basically it's just -1, -1 because why? Okay, because remember, okay, for different eigenvalues, their eigenvectors must be orthogonal. So you don't need to do anything. Okay, it's guaranteed like they are orthogonal. So you don't need to do anything, but what you only need to do is to divide its length together like U3. Okay, so this is this is W3. Okay, and then your U is this one. Okay, this is W1, this is W2, this is W3. Okay, and the UHAU, you have like this is eigenvalue -1, -1, and 5. That's it. The last one, okay. Some non-Hermitian matrices possess complete orthonormal sets of eigenvectors. Okay. For example, skew symmetric and skew Hermitian matrices. What is skew symmetric? Skew symmetric is like those matrices that A transpose equal to -A. Okay. Skew Hermitian matrix is the matrix that AH equal to -A. Okay, for this type of matrices, they could have like what should I say, like their eigenvalue could be imaginary. Okay, could be imaginary. So far, all the eigenvectors, all the eigenvalues, the examples that we have seen, the eigenvalues are real, but the eigenvalue could be imaginary. Okay, especially for the case of skew Hermitian. Okay, we can even prove that like all the eigenvalues of like skew Hermitian matrices are imaginary. Okay, the proof goes similar to the one that we proved the Hermitian matrix. The eigenvalues are real. Remember, we did that proof. Okay, so the skew Hermitian, okay, the eigenvalues are imaginary. You can check it out by yourself. Okay, but anyway, okay, so if if A is a matrix with a complete orthogonal set of eigenvectors. Okay. Now be very careful. Okay. We just say it's a matrix with complete orthonormal set of eigenvectors. So then the A equal to U D U H, where U is unitary and D is a diagonal matrix. Okay. So in general, DH is not necessarily D because yeah, D is diagonal, but the issue is this diagonal matrix, the diagonal elements are not necessarily real. If the diagonal elements are real, then DH equal to D. But if the diagonal elements contain some imaginary values, then okay, DH obviously is no longer D. Okay. And we also have AAH equal to AHA. Okay. Why? Because A and AAH, okay, if A has a complete orthonormal set of eigenvectors, then A equal to U D U H, right? So AAH is U D U H, and then UH U D H U, okay? And then you multiply them together. These two cancel out each other. So it becomes U D D H U, okay? U D D H U. Sorry, U D D H U H, UH. And then AHA similar, okay? It will become U D H D U H. Okay? The left part is the same, the right part is the same. The center part, DDH and DHD, remember, D is a diagonal matrix, right? Because D is diagonal, DHD and the DDH will be the same. Okay? We know remember, here I'm not saying DH equal to D, okay? DH and D are maybe different. But if it's diagonal matrix, say this is like A1, A2, AN 0. Multiply B1, B2, Bn. We know the result will be A1, B1, A2, B2, AN, Bn, right? Right? So that is why DHD and the DDH, they are the same. Okay, because this is simple multiplication regardless of the order. Regardless of the order. Okay, so that is why this one AAH and AHA, even though the center part looks different, but they are the same. Okay. Okay. The last one. A matrix A is said to be normal if AAH equal to AHA. Okay. And then we have this last theorem. Okay. A matrix A is normal if and only if A possesses a complete orthonormal set of eigenvectors. Okay. So if matrix possess complete orthonormal set of eigenvector, I mean, we have like a T equal to U H A U, right? Well, it doesn't. I mean, we know like for any matrix A, I mean, we have that. We got it. This is from like a Schur theorem, okay, Schur decomposition. Okay, for any matrix, we can find a unitary matrix U that does this. T equal to U H A U, where T is upper triangle, U is a unitary matrix. Okay, then okay, you can see TTH is going to be, because T is because T is U A U H, right? So U H A U. U H A U. So TTH is going to be U H A U times TH is going to be UH AH, and the UHH is going to be U. So these two cancel out each other, so it's going to be UH AH U, right? And remember, AH equal to AHA, right? This is what we are given. A is normal. Okay, we want to show A possesses complete orthonormal set like that. So A is normal. So we know AH equal to AHA. So in other words, TH, okay, for similar reason, it's going to be UH AHA U, okay? So you can easily show that TTH and THT, are the same because the center part, AAH and AHA, is given to be the same. So we know like TTH and THT are the same. Okay, and then because they are the same, remember T is a diagonal matrix, right? T is a diagonal matrix. Okay, upper diagonal, by the way. Sorry, upper triangle. What I told you. T is upper triangular matrix. Okay, so let's concentrate on the diagonal element of T, TH, and THT. We get this one. T11 squared plus T12 squared, blah, 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 plus T1n squared equal to T11 squared, and so on, blah, blah, blah. So because these are squared, right? So they are greater or equal to 0. So the only possibility to make this n formula to be equal is that, only the T11, T22, and Tnn, they are non-equal. All the others must be equal, must be 0. Must be 0. So it follows that Tij is 0, whenever I is not the same as j. So U diagonalizes A, and the column vectors of U are eigenvectors. then we have this no matrices like stuff. So that's it for section 4. Okay. The last one is section 5, single variable decomposition. Okay. This one. Okay. What is single variable decomposition? Okay. It tells you that any n